is result discussion and analysis for this project. As we can see here, this is the result for boost converter in waveform. This is the waveform that I obtained, which is the voltage output, inductor voltage, and inductor current. As we can see here, inductor voltage and inductor current that we obtained from the simulation are similar with the waveform that we refer to theory in Power Electronic Handbook written by Muhammad Rashid, and it also states in DC to DC boost converter designed for solar electric system written by Asma Rashid Poniran and MS Fattah. So we can consider that this boost converter is work properly. Next, for output voltage, from this waveform, the value of output voltage is 41.92 volt. Next, from the mathematical calculation that we made, the output voltage that we gain is 42 volt. 42 volt and 41.92 volt is slightly similar, so we can consider that the output voltage that we gain from this simulation is correct. Before we proceed to simulate the boost charging scheme with CCCV concept, we need to determine the duty cycle and resistance for the system. The first graph shows SOC versus time of charge with different duty cycle. So the duty cycle that we simulate is 0.6, 0.7, 0.8 and 0.9. From the observation, we can see that the greater duty cycle, the longer time taken to charge a battery. We also consider that the charging scheme became unstable and inefficient with a high duty cycle. It also proved by S. George, M. R. Hassan, A. Mahmood in their paper titled as Proposing a Technique to Design a Boost Converter Based Charger and Analysis of the Power and Efficiency. Therefore, 0.6 is a suitable duty cycle for this boost charging scheme with CCCV concept. Some of boost charging parameter value is slightly different with basic boost converter circuit simulation because some value are only suitable for electrical load but not proper for battery charging scheme, and it also may affect the result. For example, the resistance used in boost converter is 21 ohm. As we apply the 21 ohm to the boost charging scheme simulation, the response to charge the battery became slower. We also can see here the increment of SOC is very small. Therefore, the value of resistor was not same and adjusted to 0.1 ohm. So we can conclude here that large value of resistance can give a big impact of charging time for battery. In this section, I will present about the result of boost charging scheme with CCCV concept. The result will consist of SOC, voltage output, voltage input, ambient temperature, and cell temperature. As we can see here, the initial of SOC is 50% and increasing until minutes to 51.64%. And we can see the cell temperature also increased from 20 Celsius to 20.64 Celsius. This is the waveform that I obtained from the simulation. This is the SOC and this is for cell temperature. The average increment for SOC is 0.32% within 5 minutes. For cell temperature, the average increment is 0.128 Celsius. Next, same procedure as the boost charging scheme with CCCV concept used for this fast charging scheme, which is before we run the charging scheme circuit, value of capacitor need to be determined. The circuit was simulated with different value of capacitance, which is 50 microfarad, 100 microfarad, and 200 microfarad. Based on this graph, we can see that 50 microfarad capacitor help the system to charge the battery more faster and produce stable pulse. A response system towards battery performance, which is time of charge and cell temperature when value of capacitors varied. The highest capacitors, 200 microfarad, show a slow response of cell temperature increment. In other hand, 50 microfarad, which is the smallest capacitance, give a quite drastic increment in terms of cell temperature. So, we can conclude that a higher capacitance value will give a good feedback of charging in terms of a state of charge, but the response inversely for cell temperature. So, a 50 microfarad capacitor is a suitable value for fast charging scheme because it provides a fast response of charging. The result obtained from fast charging scheme, as observed, SOC increasing from 50% to 53%, 53.66% SOC within 5-minute charging. The increment of SOC is not constant, but it gave a better increment rather than boost charging scheme. The average increment for SOC is 0.732% within minutes. For advanced charging scheme, the cell temperature increment increased from 20 Celsius in the beginning of charging to 26.70 Celsius. The total increment for cell temperature is 6.7 Celsius. To be concluded, using fast charging scheme, the battery charged immediately as shown in a graph for SOC and cell temperature. Cell temperature during charging is quite high compared to previous conventional charging scheme. With constant ambient temperature, the cell temperature during charging increased drastically until 26.7 Celsius. Within this time of charge, the cell temperature still in safe condition and doesn't overheat. But for a long duration of charging, it will exceed the nominal temperature for battery and may lead the battery to overheat or explosion. Estimation for charging time and cell temperature made for 0% to 100% SOC of lithium-ion battery. The blue line indicates of boost charging scheme, while the yellow one is pulse charging scheme. As observed, SOC of battery increased to full charge using pulse charging within 1 hour and 50 minutes. But for boost charging scheme, time taken to charge the battery until fully charged is around 5 hours. We can see the obvious difference between these two charging schemes by this graph. Pulse charging scheme can charge the battery 30% faster than boost charging scheme. Next, as we refer to graph of cell temperature versus SOC, we can see that the final temperature of pulse charging scheme is 131 Celsius, while for battery that charge using boost charging scheme, the final temperature is only 32.8 Celsius. So, in terms of cell temperature, boost charging able to charge a battery in a safe temperature, which is between 0 Celsius to 45 Celsius. This safe temperature for battery during charging is referred to the reference that titled Guide to Understanding Battery Specification, and another reference is titled as Lithium-ion Battery Technical Handbook written by Panasonic. Cell temperature for pulse charging scheme considered as high and it may damage the battery properties. Usually, temperature will increase during charging process because charging is a process of injecting current and charge into battery. So, the higher current injected by the charging scheme, the higher cell temperature can get. Conclusion: from results that obtained, charging a battery with boost charging scheme with CCCV concept, the average increment of SOC is 1.64%, while increment for cell temperature is 0.64 Celsius within 5 minutes. Value of duty cycle and resistor used in circuit must be considered so it can charge the battery efficiently. Next, for pulse charging scheme, the SOC increased 5.56% and the increment of cell temperature is 15.73 Celsius within 5 minutes. A better pulse charging system also influenced by capacitance applied in the system. Estimation of time taken to charge also made from 0% to 100% SOC, and the results shown that the pulse charging scheme able to charge a battery within 1 hour and 35 minutes, while boost charging scheme with CCCV concept can charge a battery in 5 hours. In terms of cell temperature, also has been estimated using specific formula. The results shown that with boost charging scheme with CCCV concept, temperature of cell rise 32.8 Celsius, while the other proposed charging scheme is 131 Celsius. Comparison weight and the outcomes are firstly, in terms of charging time, fast charging is the best charging scheme because it can charge a battery in short duration. However, backdraw of this charging scheme is cell temperature during charging process is too high. This disadvantage can be reduced and controlled if the proposed charging scheme improved with controller in future. Overall, this project has been successful in achieving the objectives required. For the recommendations, there are many recommendations can be suggested to upgrade the output result and circuit development for this charging scheme. The recommendation shows as follows. First one, calculate the specific properties of battery first, such as minimum and maximum discharge current before design a charging scheme. Number two, apply more controller, especially for the cell temperature, so the scheme can adjust and control the temperature and also avoid the overheat experience during charging. Number three, add a cooling system for battery so overheat cell can be reduced wisely. Lastly, use another software like console to investigate the cell temperature of the battery. That's all from me. Thank you.